All right, well, here we go with a little math review by popular demand. Actually, somebody was requesting a brief review of some mathematics, and I'm going to put together a little bit more stuff, but I wanted to go ahead and just put this out here so that you guys would have some things. I know right now it's kind of confusing because y'all are in clinic 5 days a week, and so all the stuff that we're doing is going to have to be asynchronous. That might change in the coming weeks. Technically, I've got my fingers crossed that it doesn't, because I really want you to be able to finish out your clinical work, and we can do the laboratory and classroom part like we have been doing in an asynchronous kind of a mode. But here we go with a little review of some mathematics. First question is, if the exposure factors used are 85 kVp, 400 mA, and 12 millisecond, and those yield an output exposure of 150 milliroentgen, what is the milliroentgens per milliampere seconds, MR per mass? Now, by way of explanation, this question comes directly off of one of the registry review books. And so this thing is not written by me, but this is how you might see things on the registry. They don't word their questions the same as I would, but that's okay. With a little bit of critical thinking, we can figure this all out. Okay, so now that you've had a little bit of time to think about it, and provided you weren't paying attention, what do you think? Okay, well, I kind of gave it away with a mistake on my part. I had the answer in here, so as you know, the answer is D, 31 milliroentgens. And here's the explanation. In order to calculate your MR per mass, it's just a straight up division. All you got to do is figure out the mass that you're using. In this case, they've kind of tricked us up with the 400 mA times 0.012 seconds, which is 12 milliseconds. So if you multiply that out, you come up with 4.8 mass is what they were using. And we've measured it with a lab, like an ion chamber like we have in our laboratory. And then we take that and divide that by the mass that was selected. So MR per mass literally is the milliroentgen output per mass. For every 1 mass of X-ray quantity, how many milliroentgens is your machine generating? Now, it just so happens the machine down in our lab generates about 100 milliroentgens per mass, and our portable machine does about the same thing. So our generators are pretty strong. Anyway, in this case, we have 150 over 4.8, which is about 31.25, and so 31 is the answer. It's the closest to the actual value. Now, here's another registry question. If a high voltage transformer has 100 primary turns and 50,000 secondary turns and is supplied with 220 volts and 100 amps, what are the secondary voltage and current? Sometimes they'll ask you these kind of questions where you have to figure out the voltage and the current in order to be able to make a correct selection. But, okay, using a little bit of critical thinking, if we have 100 primary turns and 50,000 secondary turns, well, this is a step-up transformer. And what do we remember about a step-up transformer? It increases the voltage. Okay, so if I've got 220 volts, looking at my answer selections, well, right away I can get rid of A and C because those are actually a drop in voltage. So I know those can't work. So I'm left with B and D. So then what I have to do is figure out, okay, which of these has the correct amperage? And if I do my math, I'll figure out that it was B, 200 mA. And here's how I did it. Remember that formula, VSVP, voltage secondary over voltage primary, is equal to NS over NP, where N is the number of turns on the transformer coils. There's going to be a primary side and a secondary side. And the secondary side is typically bigger. It's always bigger on a step-up transformer. Okay, so we can set this thing up. Vs over 220 is equal to 50,000 over 100. Do our cross multiply and divide trick, and that gives us 110,000 volts. Then the other part of this, remember the formula for amps, and you might want to write this down somewhere. IP over IS is equal to NS over NP, where I is the amperage. Okay, so if we plug in our amps, which was 100 to start with, then we come up with 50,000 over 100, and we're going to cross multiply and divide to get 0.2 amps or 200 MA. So, okay, if you're looking at these things, remember, with a step-up transformer, your voltage is always going to go up, usually by a lot, and your amperage has to go down by the exact same proportion. So if you're going to multiply your voltage by 1,000, you have to divide your amps by 1,000. So a lot of times those numbers are getting really, really small. All right, here's another one off the mock registry. If the primary coil is supplied with 220 volts and has 400 turns, and the secondary coil has 100,000 turns, what will be the voltage induced in the secondary coil? Okay, same deal as before. We've got to think, okay, Vs over Vp is equal to Ns over Np, and if we do a little mathematics, we'll figure out that the answer is 55 kV. B. Okay, and here's how I came up with that. Vs over Vp is equal to Ns over Np, and if I just plug in my numbers that I was given, cross multiply and divide, and the answer is 55,000, which is the same thing as 55 kV. Pretty straightforward if you remember the formulas correctly. All right, in a certain grid, the strips are 8 millimeters in height with a 0.5 millimeter interspace. What is the grid ratio? Now, by the way, I had to convert this problem into word form because it actually had a picture of the grid strips, and it had 8 millimeters high with a 0.5 millimeter interspace. But, you know, I didn't really have a way to copy that picture into my PowerPoint, so I just wrote it out in words. Okay, but given all this, and oops, I accidentally let slip that the answer is 16 to 1. Okay, so if you jump down to the answer part and got that right, then good job. Now, grid ratios. These things are easy to compute, but you just have to remember what you're talking about. Those little lead strips have a height, and you know they're usually like anywhere from 3 to 8 millimeters in height. And then you have to figure in the interspace. How far of a distance is it between those strips? And these things are usually packed together pretty darn tight. So in this case, we have 8 millimeters divided by 0.5, and if you do that on your calculator, you'll figure out that it's 16. So 16 to 1. All right, here's another question. Now, this is not going to be a computational type thing. This is just can you remember thing. What is the voltage ripple associated with a 3-phase 12-pulse generator? And if you remember what those pulse waveforms look like, then this would be kind of easy because 12 pulse is a lot. Okay, so that means that the waveform stays really close to 100% all the time. So just in case you don't remember, the answer is A, about 4 or 5%. It depends on who wrote the question. They might say 3%, they might say 5%, but remember it's going to be in low single digits. So pick that one. What if you saw something that said 1%? Okay, well 1% ripple is not possible with three-phase equipment, standard three-phase equipment, but it is very possible with a high voltage generator. High voltage is about 1% ripple. This one down here at the bottom, see where it says D 100%? That would be associated with a true single-phase generator. Those things are old school. You're probably never going to see one. If I ever find one, I'll let you guys know. How many half-value layers will it take to reduce an X-ray beam whose intensity is 78 Roentgens per minute to intensity of less than 20 Roentgens per minute? Okay, oops, I accidentally put the answer for you. The answer is 2. Y'all would have probably figured that out pretty quickly, but I'll give you the explanation for it anyway. Oh, hang on, I need to back up. Okay, remember, we've got 78 Roentgens to start with. So our first half-value layer is going to cut that number down to 39. Okay, remember, that's half-value layer number 1. Second half-value layer is going to divide that 39 down to 19.5. Okay, so now we're below 20, and that was the question. They're not asking how to reduce it to 20. They're saying how to reduce it to below 20. And so 2 half-value layers will do it. Okay, if the distance from the center of the mirror, this is inside the collimator box. If the distance from the center of the mirror to the focal spot is 6 inches, what distance should the illuminator's light be from the center of the mirror? Okay, remember that mirror is mounted in the collimator box at a 45-degree angle. The focal spot is above it, shooting through. The light source, your little light bulb or your LED, is going to have to be over to the side at exactly 90 degrees offset, and it's shining towards the mirror. All these angulations have to be correct. So, given all that, what do you think? Should it be 3 inches, 6 inches, 9 inches, or 12 inches from the mirror? Okay, well, it turns out the answer is 6 inches. And this totally makes sense when you think about it. And this is a critical thinking kind of a question. I don't remember actually reading this in any textbook, but I can kind of figure it out if I think about what's going on. You just have to remember that the geometry of the light and the X-ray beam are virtually identical. Okay, so even though light can't pass through material and X-ray can, and light can be reflected and X-rays cannot, other properties they hold in common, including the inverse square law. The farther you get from a light source, the dimmer it is. It works exactly the same way. So a lot of the rules regarding how these beams fan out are identical. So you've got to set it up so that the geometry of your X-ray beam and that of your light field are as close to identical as possible, given our mechanical constraints, because these mirrors, sometimes it's really hard for the repairman to get the mirror adjusted exactly 45 degrees. Or the light bulb, maybe the light bulb socket's a little bit crooked, and that's going to throw off your light field. You may have been at a clinical site where the light field and the X-ray field don't exactly match, and nobody can seem to figure out what the problem is. And that's because, if you look in there and it looks like the light bulb socket is perfect, if it's canted by like 1 degree, that can wind up throwing off your light field and make it not match with your X-ray beam. Okay, during a fluoro operation, it is found that exposure at a range of 8 feet from the patient is 2 Roentgens per minute. What would be the exposure if we move to a position 2 feet from the patient? Okay, so if we're going to move from a distance and we're moving closer to the patient, we know that our exposure is going to go up, but by how much? And I'm just really messing up today with these fly-ins. Okay, so the answer is D, 32 Roentgens per minute. Okay, so let's find out why. Okay, remember, the inverse square law rears its ugly head and bites us in the hiney. The rule, exposure 2 over exposure 1 is equal to D1 squared over D2 squared. So if we plug in our values, we're going to wind up with, remember, we started out, E1 was 2 Roentgens. We somehow measured that distance at distance of 8 feet. Okay, and then 8 times 8 is 64, and 2 times 2 is 4 if we're plugging in our numbers. And so cross multiply and divide, and we get 32 Roentgens per minute. Now 32 Roentgens per minute would be off the chain. If there's that much energy coming off the patient, then there's a there's a bad issue. Or you're standing next to a nuclear furnace. Okay, so we've been doing some experiments in the lab, as you might remember, and I've up and decided to make an executive decision. So, given our lab results, from now on I'm using a 50-inch SID unless somebody comes along and tells me not to. You got to do what the boss says. And if the RAD doesn't like it, then the RAD doesn't like it. You're not allowed to do that. But if nobody says anything, I don't see why, as a professional RT, I shouldn't be using a 50-inch SID whenever possible. So what changes do I need to make? Now remember, I'm going to be using 50 inches for every exam that I possibly can. That's everything from a finger to a foot to an abdomen. Whatever I used to use 40 inches, I'm going to use 50 from now on. And let's assume, just for the sake of making things easy, that I've been using 100 mass all this time. So what's going to be my new technique? Am I going to need to increase it or decrease it? Because I'm increasing my distance by 10 inches. So yeah, I'm going to need to increase my technique. But by how much? Okay, so my old distance was 40 for most everything. Chest I'm going to leave alone, because now I could change that too. I could say, okay, well, from now on, instead of 72 inches, I'm going to use a range of 9 feet, or something like that. The benefit wouldn't be worth it. At this long distance, if I increase my SID more, will I decrease my magnification level? Yes. Will it be significant or even noticeable? Probably not. So not really worth it. 72 inches for chest work, that's fine. I'm going to keep on doing that. Okay, mass maintenance formula. Remember this. Mass 1 over mass 2 is equal to D1 squared over D2 squared. This time we're a direct relationship instead of an inverse one. Okay, so if I'm plugging in my numbers, I've been using 100 mass all this time, so my mass 1 is 100. And then for my distances, my original distance was 40 inches. You square that, you get 1600. Distance 2 is going to be 50 inches. Square that, you get 2500. And doing a little cross multiplication, we come up with 156. Now, since we're talking about hundreds, we can also talk about percentages. So that means that I need to increase all my techniques across the board by 56%. I'm just going to say 50%, for ease. So like, for example, if I was using 12 mass for an X-ray before, I'll use 18 from now on. And you're like, okay, well, wait a minute, aren't you going to heat up the patient? Probably not, because as you've noticed from our work in the laboratory, whenever we increase our SID, we drop our entrance skin exposure, even though we're compensating in technique. And sometimes we're increasing our technique by 2, we're increasing our technique 100% and still seeing the ESC go down. So, this is in the patient's favor from an exposure standpoint. Okay, and yeah, just wanted to let you guys know, no, I don't shoot all my X-rays at 100 mass. That would be very, very lazy. And as a matter of fact, I was thinking this to myself. Anytime your mass is entering triple digits, you'd need to look at your KV. What's wrong with your KV? Is that thing set at like 70 or 75? Why are we using all this mass? Now, if your KV is already set at like 120 and your image is still underpenetrated, okay, well, then you got an issue there. How far can you push your KV and how far can you push your mass? But rule of thumb, in general, if your mass is that high, then look at your KV and see if it makes sense. And ask yourself, well, if I kick my KV up to 100 or 110 for this spine X-ray, can I compensate down with my mass? This is the kind of critical thinking that you have to do all the time for the patient's sake. All right, y'all, so that was it for my little math review, and this has been about 20 minutes, and hopefully didn't bore everybody to death. So I'm going to post this up, and I'll also yeah, I'm going to also see if I can't find you guys some more math problems that you can work on, and then maybe we can discussion board those things or flip grid. I like flip grid. All right, talk to you later.